Hi there, everyone. So I'm here as the chair for today's session. Before I start, I'm going to mention that this is being recorded. If you don't want your image and voice to be captured, you're welcome to turn your video off, and any questions that are posted in the chat, I will relay to Doug at the appropriate time. The second thing is, if you are getting a closed caption transcript and you'd like to turn it off, there's a little button at the bottom of your window with CC, which you can press to remove the transcript. Okay, so welcome to the first seminar of the Applied Mathematics Theme Week in the Newton Institute program. I'm really happy to introduce Doug Wright. Doug finished his PhD in 2004 at Boston University under Eugene Wayne, and he's now on faculty at Drexel University in the US. And he's here to talk to us about traveling waves in diatomic granular chains. Thanks very much, Doug.
Great. Thank you for the introduction, Chris, and thanks for the invitation to be here. So I understand that this workshop is part of a bigger thing about sort of asymptotics and beyond all order sort of phenomena, and that this talk is going to have some of that in it. That's kind of why I know Chris, is because he has worked on this more or less this exact same problem from an asymptotics angle, and he's seen this talk I think at least once before, and he knows the work quite well, but I thought I would talk about it anyway because this is really the main thing that I've done in that area. This work is joint with Aaron Hoffman, and it's a couple years old at this point. So let's get into it. Why did it not move? There we go. So I'm going to tell you what everything is first. So here we go. This is the physical apparatus that I'm going to talk about. It's called I call it a diatomic Fermi Pasta Ulam&ndash lattice. All right. So what it is you have a bunch of masses. You have a big mass, which is blue, and you have a little mass that's yellow, and they're arranged every other one on a line, and each one is connected to its two nearest neighbors by a spring. So you can see here the sort of coordinatization that I'm doing here. Yj is the position of the jth mass. So I guess here the odd ones are big and the even ones are small. The relaxation length of the spring I'm going to call L. So it doesn't really play much of a role in what's going on, but I like to put it in just to keep people grounded. So each spring has length L, and Rj. The Rj's are just the deformation of the spring relative to that length. So Rj is something like Yj minus 1 minus L. So each of the springs here was made by a manufacturer who's really good at making springs that are all identical. So each spring has the same restoring force, which I've assumed here is the sort of standard FPU restoring force. I think it's called the alpha model in the original FPU literature. It's got a linear part, which is our usual Hooke's law thing, with a quadratic addition to it to make it nonlinear. If these little yellow masses had mass 1, then this would be the classic Fermi Pasta Ulam problem. But we're changing it so that it has this sort of diatomic sort of flavor to it. And sometimes when you see this in the literature, sometimes they call this the NaCl chain, meaning like salt, like a sodium molecule. I don't know how legitimate that is. I don't think a chemist would really view this as being that sort of being a particularly realistic model for that, but that's what sometimes people call it. And anyway, here's the situation. These guys are lined up on the line. They're allowed to move left and right, but not up or down and not out of the screen. There's no friction or damping or anything like that in the problem, and so you can get the equations of motion just from Newton's law. Hey, this is talk at the Newton Institute. I feel pretty cool about that, actually. It's like the most minor thing that ever happened, but I'm strangely pleased by this. And so it's just, MA equals the difference of the forces, the one on the right and the one on the left, or the left and the right. There's a minus sign over here, and that might be why these look a little bit funny. But those are the equations of motion, and that is what we're going to study. Okay, let's go on to the next slide. So the question that I want to answer is if there's solitary wave solutions in this system. So when I give this talk, not everybody is familiar with these sort of lattice differential equation problems. I mean, there's infinitely many of these guys. This is an infinite dimensional problem. These guys go forever, both left and right. And so sometimes people don't have a good visualization of what they mean by traveling wave in this sort of system. For a PDE, people generally know what they're talking about, know what people mean, but sometimes they don't get it for this one. So I made this little cartoon for this. So the idea is like, here's our chain, which I've just put a snippet here, and you sort of squish the leftmost spring, okay? And so what does that leftmost spring do when you squish it? Well, it unfolds, right? It unfolds and it pushes that mass to the right by a little bit, but that of course squishes the next spring. This is, I mean, an extremely simplified cartoon of what's going on here, but this is kind of how it works. This spring is squished, it unfolds, it pushes that mass, that one unsquishes, it pushes that one, and so on and so forth. And so if you go into like a sort of time space plot of this, so these are the same exact frames that I showed you before. Time is going downwards. The first slide is at the top, the last slide is at the bottom. Position is sort of left, right. And then what I'm going to superimpose over this is how squished the springs are. So a squish spring is represented by a bump up, and if it's unsquished, it's just a sort of flat thing right there. And you can sort of see the solitary wave moving left to right. Okay, so I usually include this just to give people a sort of idea of like what physical phenomenon we're looking for. All right. It's a little bit like the Newton's cradle thing, that toy that you play with, right? All right. So let me tell you about what is known for the monatomic problem. So when I say monatomic, I mean every mass is the same. You don't have this alternating big, little, big, little. They're just all big. Okay. So Garo Frieseke and Jonathan Wattis, I think this was in the 90s. They wrote a very influential paper about the existence of solitary waves in the monatomic problem. So basically what they proved is that for all speeds bigger than 1, that's the speed being, what you would consider the real speed. And of course, this is all normalized, so all the coefficients turn out nicely. For all speeds greater than 1, you have a solitary wave like the cartoon I just showed you. All right. And as the speed c approaches 1, the amplitude of that wave goes to 0 and it spreads out. That is to say, it has a long wavelength. Now, here's the observation that Aaron and I had is that if you pull out every other one, if you pull out every other mass, right, and you just reconnect the springs, it's still a monatomic lattice, right? So there's the monatomic lattice. You remove every other one and you reconnect the springs, and so now it's the same problem, only I've got a different sort of spring. I've got a spring that's twice as long as the previous one, and that just mucks around with the inner the spring force a little bit. So it's really the exact same problem that Frieseke and Wattis studied. And so if you remove every other spring and you look at their results, you find out that there are solitary waves in the monatomic lattice where you put this little guy to 0. But now the sort of minimum speed has gone up to be the square root of 2. Okay, you just kind of dig into their papers and you figure all this out. It's not so exciting. Okay, so what I'm interested in is like, okay, I pulled them out, right? And I have a solution in this case. I have a solution here, traveling wave solution, and then I'm going to put that little yellow particle back in between. Okay, so are there solitary waves in the diatomic lattice when we have 0 less than mu, much less than 1? And so the answer to the answer to the question, this is our theorem, is that there's sort of yes, there are sort of solitary waves. So what do I mean by sort of? What I mean is that they're nanopterons. And so I think some people in the audience know what people mean by nanopteron, but I don't know that everybody does. So what I'm going to show is some movies that sort of illustrate what this means in this context. So just give me a moment to follow these guys up. So I'm going to show you 4 movies. Okay, so here's this first movie. This is really just my attempt at being animating that cartoon I showed you. So here we have the particles. This is the monatomic problem. They all have the same mass. I should have colored them blue to be consistent with my cartoon from earlier, but I didn't. They're green. And you can see I've bunched them all up over here. And then when I run it, you sort of see this this movie version of what I showed you before. I want to be clear here, these are not numerics. I didn't actually solve the KdV or the FPU equation numerically and do this. I just kind of cobbled something together just to give ideas. So this is really just qualitative stuff right here. It's not to be taken too seriously. If you plot over top of this, the sort of compression of the jth spring, so let's say that the spring has length 10 here. So when they're perfectly far apart, this blue line is at altitude 10. And when they bunch up, it goes down and then it propagates. And you can sort of see the bunching up where that is. And so that's the solitary wave that I'm talking about. So that's the solitary wave. That's the monomer problem, the monatomic problem. Let me show you a similar cartoon for the diatomic problem. And again, this is just qualitative. This is not meant to be, I didn't do simulations here. And you'll see that there's something quite different right here. This is what our theorem is going to say. It says that you have the same sort of squishy propagation going on, but there's this superimposed wiggle at infinity. All right. So it's sort of a traveling wave, sort of a solitary wave plus a wiggle, which we're going to call a ripple in a moment. And if you do the same sort of plotting the compression over top of it, you get this guy right here. And so I don't know if you can see this on your screens, but there's our solitary wave just as before. And you see there's this little like ripple out here. This little guy right here. Turns out that ripple is also co-propagating with the same speed as everything else, but it sort of, to the naked eye, appears like a vibration, right? So that is the sort of thing we're looking for. So if you get nothing else out of the talk, you get that little video there of what we're proving. Okay, the solitary wave turns into a solitary wave plus a vibration when you go to the small mass problem. All right, I've got to say some stuff about other results in the diatomic FPUT problem. We were hardly the first people to look at this problem. One thing that a variety of people have studied is that in a sort of long wave limit where you're looking at solutions which cover many particles, like you have a wavelength that covers like a lot of particles at once and are not too big, you get a KdV approximation. The earliest stuff is this by I believe he was an engineer named Nevmatikos. Kyrillis-Bruckner and her collaborators proved a rigorous result for the diatomic problem, and then for a polyatomic problem, Jeremy Gazen, who was an undergraduate researcher with me at the time, and I and several others proved a similar result to the Kyrillis-Bruckner result. And everybody knows that KdV has solitary waves, and so this was sort of giving us the idea that even in the polyatomic problems, we should see solitary waves. Betty Pelinovsky, Chin, and then Tim Favor and I proved that there were spatially periodic waves in the diatomic and polyatomic problems, or just the diatomic problem, I should say. Anna Weinstein and I, and then also Chris Lustry with his collaborators, this is how Chris and I got to know one another, provided sort of detailed asymptotics and numerics for the traveling wave problem in the mu to zero limit. I'll talk a little bit more about those results and how they compare with our results in what comes later on. And then Tim Favor and I, for this was his PhD thesis, we proved the existence of barely supersonic nanopteron solutions for fixed values of mu. So if you pick mu to be any number you want in between 0 and 1, so I'm going to call that the mass ratio, so the ratio of the two masses. And then you don't care about mu being small. It could be small, it could be big, whatever, but you fix it. And then you look for what are essentially slowly propagating waves, waves that propagate with small amplitude just above what is called the speed of sound. You can do an argument there to get nanopteron solutions. Kind of looks the same as what I'm talking about here, but it's kind of a different limit, right? So in a technical way. So let me give you my technical statement of the theorem. To do that, I need to introduce some coordinates and make sure that we're all on the same page about what we're looking for. So here's a snippet of my lattice. I've sort of tried to show it sort of in a dynamic position where this little guy is like over far on the right. So this spring here is compressed and this one is sort of stretched. So what you do is you go to two big particles and you figure out the midpoint between them. All right. So I'm going to call the midpoint between the jth big guy and I guess the j plus second big guy. I'm not going to call the midpoint. What I'm going to call is the distance to the midpoint between two big guys. I'm going to call that h1j of t. All right. So the distance from the jth particle to the midpoint between it and the next big particle is called h1j of t. So roughly speaking, if you knew h1j for all j, you would be able to figure out where all the big blue particles are, right? If I tell you, it's basically me telling you what's the distance between the big blue particles, right? Except if I divide that distance by 2. Okay. So you kind of know where all the big blue particles are, and then I'm going to tell you where the little blue particles are relative to that midpoint. All right. So the H1 tells you where all the big blue particles are, and the H2 tells you where the little blue particles are. It's kind of an unusual choice of coordinates, but it turns out to be a good one. All right. So if you know H1 and H2 for all j, then you know where all the blue guys are, and you know where all the yellow guys are. And so you go through and and then I'm looking for traveling waves, right? Since I'm looking for traveling waves, I want to go into sort of co-moving frames. So instead of having functions which depend on the integer j and the time t, I'm going to put it into a moving reference frame, j minus ct, where c is going to be the wave speed. Okay. So you use these coordinates plus this traveling wave ansatz. I call my traveling wave coordinate x. That's a continuous thing because t is continuous. And I plug that into everything. Oh, just a little lingo. Since h1 tells me where the big particles are, I'm going to call it the heavy variable. And since h2 tells me where the little guys are, I'm going to call it the light variable. You grind that into Newton's law, you do a bunch of algebra, and you get something that looks like this. All right. So the first equation there I'm going to call the heavy equation because it's the one that I sort of view as telling you what the heavy equations are doing. Of course, everything's coupled between heavy and light. And the second one tells me where what the light particles are doing. Those second derivatives there, that's the Newton's law stuff. Of course, I went into the moving reference frame. So time derivatives become c squared times, well, the traveling coordinate derivative. So primes are derivatives with respect to x here. So let me talk a little bit about what you're seeing here. So these are really just Newton's law and the co-moving frame. These two different equations. What is A and what is delta? Well, what you do is you go to a point X, you look forward by 1, you look backwards by 1, you add this together and you divide by 2. So it's a sort of an average of what the function is, 1 unit to the right and 1 unit to the left. So that's why I use the letter A here. It's like an average of what's going on there. And delta is like a finite difference. You look to the right by 1, you look to the left by 1, you take the difference and divide by 2. And this, I mean, these are the relics of the nearest neighbor coupling in the problem, right? The particles are coupled with nearest neighbors. So you look to the right, look to the left, and that all shows up in here in this way. So the thing I want to point out here is that this is non-local. These guys are not, this is not an ODE, right? H is not an ODE because you need to know the value of H in the future and in the past, future and past being left and right in X, okay? And this is a singularly perturbed problem. This is really one of the key difficulties here. Mu is our small parameter, and mu appears in this light equation multiplying the highest derivative in the problem. So we have a small parameter multiplying the highest derivative. That's classically singular perturbed situation. So what we have is a singly perturbed advanced delay system of differential equations. One thing I want to remark is there's a bunch of terms that come out with just mu's multiplying them that don't multiply derivatives, and they're sort of innocuous. And so I generally will label those on my slides as mu's that are green. So the green means it's safe. The red means it's dangerous, right? Okay, so this is our system of equations. It's a singly perturbed advanced delay system of differential equations. So it's kind of a complicated beast. When we move on, I want to talk about, I mean, what do you do when you see these sorts of problems is you put your mu equals 0 in there, and you see what happens. So if I put mu equals 0 in the light equation, you get this guy right here. So the gray terms are now to be viewed as 0. And I can solve this by just setting h2 equals 0. I mean, you could say that you could solve it by taking h1 equals minus half, but that's kind of a fiction. Don't worry about that. I take h2 equals 0 when mu equals 0. All right. Now that's a reasonable thing to have happen. Remember, h2 equaling 0 means that the light particles are exactly halfway in between the big particles. And that's the picture that we see when we just remove them sort of schematically from the situation many slides ago, when I said that if you remove the light particles entirely, you get another monatomic lattice. That's what happens. This is sort of reflecting that scenario. So if I do that, I put mu equals 0, I put h2 equals 0 in, the heavy equation becomes this equation right here. Now, if you're in this game of FPU traveling wave equations, you will recognize that that equation in the box right there is exactly the profile equation for the monatomic problem that Frizeka and Wattis and other people studied. Okay, so if you're not in that game, you won't recognize it as that, of course. But if you do, you say, oh, this is the monatomic problem, and I can call upon those earlier works to get a solution. And let me just describe that solution for you quickly. It's positive, it's even, it's unimodal, and it decays exponentially quickly as x goes to infinity. You should basically be thinking it looks like sec squared of x. There's some parameters in there, and it's not exactly that, but that's roughly speaking what it is. And you have a solution for of that box equation when c is bigger than the root of 2. So this is me recapitulating what I said earlier. Okay, but now I'm doing it in a sort of more precise way. So every time you see sigma c, you should be thinking it's basically sec squared. Okay, so the question is, what happens to this special solution when mu equals 0? h1 equals sigma c, h2 equals 0 when mu is greater than 0 but small. So now we're back in, I've just resaid the same question I asked earlier, but now I've got a sort of grounding and some language for it. So here's the theorem that we prove. So for all our wave speeds bigger than the root of 2, not too big, but not, you know, I don't need a limit here. I mean, it can't be 5 million, but, you know, just within a reasonable interval around root 2. There's an open set, this is where things get confusing, of positive numbers. So there's a bunch of positive numbers whose closure contains 0. And those are going to be masses. So there's an open set of masses whose closure contains 0. So I can take mu very small in this open set. And for each of the choices for the mass in that open set, we get a nanopteron traveling wave solution for the problem. And it has this form right here. So this is very specific. So the heavy variable is the leading order solitary wave that Frizeka and Pego give us, plus a to 1. What's a to 1? And what's a to 2? A to 1 and a to 2 are exponentially decaying functions with respect to x, and they're small with respect to epsilon, with respect to mu. They're order mu. Okay, this is sort of the regular perturbation piece. A to nj and a to 1 and a to 2 go to 0 at spatial infinity. And now here's the little ripple that you saw in those videos, P1 and P2. These are periodic functions of x. Their frequency is quite large with respect to the small parameter. It's like 1 over the square root of mu. And their amplitudes are small beyond all orders of mu. And this is why I get invited to this thing, because of that purple thing right there, the small beyond all orders of mu. So it's the main piece, an exponentially localized piece that's sort of order mu, plus a super tiny periodic thing. All right, that's the heavy variable, and in the light variable, it's the same thing except that there's no leading order solitary wave, right? Because the leading order part is 0, as we saw earlier. Okay, so that is our theorem. So how am I doing on time? I think I'm doing pretty good. So here's the sketch of the solution. So if you look at, let's just look at what H1 looks like. There's our set squared looking guy, sigma c. That's the mu equals 0 solution. When I turn on mu, I get I perturb that a little bit. So the sort of gross scale perturbation of the black thing here is the blue thing, and that's sort of what the naked eye sees is what I called a to 1 before. But if you zoom in very far away, I mean, you could zoom in anywhere really, but it's more cinematic to zoom in far away. It looks like it's going to 0 way out here and way out here. But if you zoom in many, many times, you get a little tiny high frequency ripple. The frequency is 1/√mu, and the amplitude is super tiny. And so when I say small beyond all orders, I mean small beyond all algebraic orders. If you give me a number n and you say, is it smaller than a constant times mu to the n, I will say yes. I'm not able to prove that it's exponentially small in mu. I have some ideas about how you would do that, but I have not done that. So you should think in your head that it's sort of exponentially small in mu, like e to the -1/mu or something like that, but that's not proven. But we do know that it's small beyond all algebraic orders of mu. All right. If you want to know what H2 looks like, it looks like the same thing, except it's an odd function that looks close to 0. All right. So what are the main ideas? So people always have questions about this, like why is there a ripple? Why is there that open set? Why is it not true for all values of the mass mu? And I should say that I don't have a proof that says that they don't exist in those places outside of my open set. I just don't. My proof only works for things in this open set. So what I want to elucidate is why is there a ripple, and why is that ripple so small, and why is there this open set thing for the masses? So those are the three things that I want to sort of try to get explained. So all the action in this problem is basically in what I call the light equation, the equation for H2, the singularly perturbed one. More or less the action, what happens in the heavy equation is, I wouldn't say it's easy, but like it's not the it's not the heart of the argument. So I'm going to mostly focus on the light equation. All right, so here's our light equation. I'm just recapitulating it for you. It looks like this. What I'm going to do is I'm going to stuff into that an ansatz where H1 is the solitary wave profile plus some perturbation. You'll notice I'm calling it C1 here. I'm not calling it A1 or P1. This is just a generic perturbation term right now. And I'm just going to let H2 be sigma 2 of x, C2 of x, where I'm basically thinking right now of C1 and C2 as being small, and let's just for the time being think of them as being localized, like the etas that I showed before. Let's imagine that they're going to 0 quickly at spatial infinity. So if you stuff in this sort of generic ansatz for the form of solution into L, and also H, but I'm not going to show you what happens in H. If you stuff it into L, you get an equation that looks like L2, right? So it's roughly the linearization of L at sigma C and 0. Okay, so you get this guy right here. So the left-hand side of this is a linear operator. I'm going to talk a lot about it. I'm going to call it S mu, depends upon mu, but it is linear in the variable C. And then the right-hand side, well, that's everything that I'm going to quote call innocuous. It turns out it's not as innocuous as I want it to be, but let's call it innocuous. It's stuff that's sort of quadratic in the C's and therefore sort of small, or stuff that has an exposed mu on it. So I can think of if mu is small, it's small. So stuff I'm gonna try to ignore. Okay. So that operator, S mu, well, it's not some crazy operator. It's just a garden variety scalar 1D Schrodinger operator. And the potential is 2 times 1 plus 2 sigma C x. If sigma C was actually a Sech squared, you would know everything you ever wanted to know about this operator in terms of special functions. It's not exactly Sech squared, but you can still basically get most of what you want to know about it. It's a pretty nice operator. So what's the kernel of this operator? Well, what's the kernel of this operator? Well, you set it equal to 0. That's a second order non-autonomous ODE. And so you can kind of get most of what you want to know about it out of ODE methods. One thing I told you about sigma C is that when x is really, really big, sigma C is 0. So if I want to know what solutions of this equation look like when x is really big, I cross out the sigma C term, in which case now it's not just a Schrodinger operator, it's a simple harmonic oscillator with frequency 2 over mu C squared. Well, that's where that 1 over square root of mu that I was talking about the frequencies comes from, right? The kernel of this operator is spanned by two linearly independent, what I'm going to call Jost solutions. You can make sigma c is even, you can assume one is even and the other one is odd. The even one I'm going to call zeta 0. The odd one I'm going to call zeta x. Zeta 1, it turns out to be the more important one for us. They are asymptotic to sinusoids with this frequency for large mu. All right. And these are the only two solutions. These are the only two kernel elements, right? Because it's a second order ODE. So what does this tell us? Okay, what does this tell us? This implies that S mu is injective in spaces of exponentially decaying functions. Why is that? Well, look, there are two kernel elements and they are not zero at infinity. All right, so if I restrict my attention to functions which are going to zero at infinity, say with some prescribed exponential rate, the Jost solutions are not in there. Since they're not in there, that means the kernel in that function space is trivial, which means that the operator is injective. One thing I want to point out here, and this is a big deal when you get down into the weeds, if you restrict yourself to, say, an L2 space with an exponential weight on it to get this exponentially decaying stuff, my operator here is not self-adjoint. It makes a difference when you get in the weeds, but it's not going to make much difference at this level. Okay, so now you have this operator, S mu. You know it's kind of injective on spaces of exponentially decaying functions, but it's not surjective. All right. So if I'm trying to solve S mu C2 equals R2, where I assume that R2 is, for the moment, exponentially decaying, I multiply that equation by zeta 1. Remember, everything's even in my problem. Or no, everything is odd in this problem. Sorry. You can assume that R2 is odd. Just trust me on that. If you multiply the equation by zeta 1 and you integrate both sides over the entire domain, well, you use the self-adjointness of the inner product in the L2 the usual L2 inner product. You move it over onto the zeta 1, it kills it off. So the left-hand side of my equation there turns into 0, and the right-hand side turns into just R2 times zeta 1. You integrate it. This is really just me saying that the range is the perp of the kernel. You got to do all this stuff with the exponential function spaces and the not self-adjointness, but really that thing there, that equation that I've called S is a necessary condition to solve equations like this. Okay, so to solve what I called L2 on the previous slide, I need that the right-hand side of whatever that is, so to speak, orthogonal to this odd Jost solution. Okay, so zeta 1 is playing a starring role in our problem. We need this solvability condition to be met. And the nice thing is that because this is zeta 1 solves an ODE, I can basically tell you everything you need to know about it. It's somewhat complicated by the fact that I'm studying this ODE, in a sort of semi-classical limit because the coefficient here is small, but you still can do it with ODE means, right? So here I just want to show you a picture of what zeta 1 looks like. It looks like a sinusoid where the frequency is sort of higher, slightly higher near the origin. The amplitude is slightly smaller, but as x goes to infinity, it sort of relaxes into a slightly longer oscillation with a slightly bigger amplitude. That's what it looks like if you were curious. Okay. The issue here, though, is that we're in a situation now where we have two equations, the heavy equation, the light equation, and a third equation, which is that solvability condition that I just discussed. Okay, so we have three equations and two unknowns. We have the equation for the heavy variable C1 equals whatever that right-hand side is. We have the equation for C2, S mu C2 equals R2, but we also have this prescribed condition on R2. So we have three equations, 1, 2, 3, two unknowns, zeta 1 and zeta 2. So basically everything I told you was what happens if you try to solve this equation in a class of functions which exponentially decay. And so the reason you get this sort of extra equation is because that was the wrong idea. All right, that was the wrong idea. You should not have done that. in the back in the early 90s, Tom Beale, pictured here, he encountered a similarly overdetermined system of equations in his study of traveling waves in the capillary gravity wave problem. If you're not in the water waves community, the capillary gravity waves problem is water waves on a canal where you consider surface tension. That's what capillary means. That's a fluid mechanical problem. It's the technicalities of that problem are quite different than what you've seen here, but the sort of on another level, it's quite similar. And that's a problem that has a KdV approximation. A lot of the stuff is sort of like, technical in the weeds, but at a bird's eye view, quite similar. So he came up with a strategy for solving this, for solving his problem that provide a starting point for us. And so I was sort of heavily promoting what I call Beale's method for problems of this type for a long time, and I still do. Of course, there are other ways to approach these problems, but I know Tom, and I knew this work, and I'm sort of a functional analyst at heart, and so it sort of spoke to me when I came across this. So okay, so here's the idea that Tom had. So you take your C1 and C2 that I had earlier, and instead of thinking them as exponentially localized, you think of them as an exponentially localized part A to 1 and A to 2, plus a periodic part. And you don't just take them to be any old periodic functions. You take these periodic guys here to be exact periodic solutions of H and L. Okay, so instead of looking for localized or sort of solitary wave-like solutions, you look for periodic solutions in H and L. Also traveling with the speed c, all that same stuff, you get some equations. You try to solve them, and it turns out that you can absolutely solve them. They sort of bifurcate from that linear solution with frequency 1 over square root of mu, and you get a family of them with any amplitude close to 0. All right. As you vary the amplitude close to 0, the frequency of the thing changes sort of proportional to A. But okay, you do a classic Crandall-Rabinowitz bifurcation from a simple eigenvalue argument, and you get a family of small amplitude periodic waves, traveling waves to the problem with amplitude A. And like I said, it's a family. Okay. So the amplitude A here is going to basically play the role of a third unknown in my problem. So what are my unknowns? A to 1, A to 2, and A. All right, A is scalar, and that equation, that solvability condition S, is basically a scalar equation. So you kind of do like a abstract counting argument on how many variables you got, and it seems like it fits in there perfectly. That was sort of Tom's observation. And A to 1 and A to 2 are going to be genuinely exponentially decaying. So I'm going to like run that story. So let me explain pretty quickly why there's this restriction on the masses. Okay, so it all comes down to trying to use the amplitude A to meet the solvability condition S. Okay, that solvability condition S looks like this. All right, this equation here on the top. It's whatever R2 is, and I've not told you what R2 is ever. It's just some messy bunch of terms. And you're multiplying it by this Jost solution, you're integrating, you're getting 0. Okay. Now R2 at the end of the day, you could view it. So what is R2 made of? It's made of all the stuff in the problem. So really what it depends on when you get down into it, it depends on A to 1, A to 2, and A. Well, everything depends on A to 1 and 2 and A. That's my, those are my variables now. Okay. So you just want to solve it by the implicit function theorem. If you put A equals 0 in this, and you put mu equals 0 in this, well, you don't really put mu equals 0 in it, but you put A equals 0 in it. Turns out it's sort of satisfied automatically, like within, well, let me say it better. If you put A to 1, A to 2, and A in this, and you put it equal to 0, it's basically 0. It's not exactly 0, but let's just act like it's 0. Okay. So you have a solution sort of at 0 for A to 1, A to 2, and A. And you want to solve it for A given the etas. That's the approach I'm going to take here. It's sort of a Lyapunov-Schmidt sort of idea, right? It's not sort of, it's exactly Lyapunov-Schmidt idea. So suppose you know A to 1 and A to 2. You want to figure out if you know A. How you do that by the implicit function theorem? Well, you differentiate your objective function with respect to the thing you're trying to solve for, and then you evaluate it at the sort of known solution. So I'm going to differentiate this expression with respect to A, and then I'm going to evaluate the whole beast at A and A equals 0. Now, and remarkably, and this was one of the craziest things that happened when we were doing this, is we realized that we needed to do this, Aaron and I, and we were actually visiting the University of Pittsburgh at the time. And we wrote, or no, I was visiting Aaron at Olin, doesn't matter, but we were like, can we compute this thing? Can we compute this quantity? It seemed like we couldn't, but we could. And you can do it explicitly, and it turns out that it's this number right here. So it's got the parameters in the problem. It's got the wave speed in there. It's got the small parameter mu in there. It's got omega mu. Omega mu, remember, is 1 over the square root of mu, more or less. It's the frequency of the, it's the sort of intrinsic frequency of the problem. And then you multiply it by sine of, again, omega mu, which is, again, large, times theta infinity mu. And theta infinity mu is the asymptotic phase of that Jost function. All right, I still can't believe that we were able to do this. It's not a hard calculation, but I still can't believe it came out. Okay, and so here's what happens. It turns out that if you get down into your Jost function and you make mu really small, it turns out that the asymptotic phase basically settles down to a fixed number. So you should think of this, it's not exactly constant, but you can basically show that it's confined to a small interval. Okay, that's an ODE thing. Okay, so this term here is roughly, just imagine that it's 1, just to keep your mind to make things easy. And then we have omega mu. Omega mu is going to infinity as mu goes to 0. So the argument of sine is like, well, just think about it as being like 1 over the square root of mu. As mu goes to 0, that obviously goes through 0 infinitely many times, right? So there's a bunch of points at which is at k mu, as mu goes to 0, where this quantity is exactly equal to 0. But there's more points where it's not. All right, so since k mu is equal to 0 at countably many values of mu as mu goes to 0, we go in and we just ignore them. We cut out all those countably many values of mu, and we're left with an open set of values of mu where k mu is totally non-zero, and we're good. Now, there's one additional complication here is that k mu is non-zero a lot of the time, but that mu times omega mu right there, remember omega mu is like 1 over root mu. That blue term that I just highlighted is small. Okay, so k mu is sometimes 0, most of the time it's not 0, but it's all the time small relative to mu. Okay, and that's a problem, as we're going to see on the next slide. This is the technical difficulty, and this caused us a lot of consternation. The strategy doesn't work, and it's related to the fact that that kappa mu term is actually kind of small. When you use the implicit function theorem, that derivative, you get a solution for small values of whatever parameter you're using, but the derivative that we just computed basically shows up as 1 over it in that solution. And so when we do that implicit function theorem argument on this guy here, the sort of thing we get for R2 or whatever, it kind of winds up being too big. There are terms that are too big for us to deal with because we're dividing somewhere by square root of mu. It's very technical, but the point is there wind up being terms in R2 that are too big for us to handle the inversion of this operator on. And all those terms ultimately came from terms that were in R2 that looked like mu times something linear. It took us a long time to sort of figure this out. So we had a pretty smart idea, which is we took all those problematic terms and we just moved them over to the left and incorporate them into the linear part. So now we have a new equation, S mu plus some order mu linear guy times the a to 2 equals, well, a new right-hand side, R tilde, where now R tilde is not order mu stuff, but it's order mu squared stuff plus nonlinear stuff, which we're going to be able to handle. And so now we have to understand this mu operator S mu plus mu gamma mu. What is gamma mu? Gamma mu looks like this guy right here. It's non-local. There's that A operator again. That's a non-local operator. And it's also spatially it's got a spatial component, spatially varying component right there. It's non-local. It's not self-adjoint. It kind of ruins a lot of the structure that we're relying on. Okay. But it is small. Okay. So, okay. What we had to do is we had to rerun the whole argument that I just described to you. But instead of having zeta 1, whatever the analog of zeta 1 is for this now perturbed operator. So we have an order mu perturbation of S mu. But remember, S mu has got this small sort of semi-classical singly perturbed term in it. It's non-local. So we got all our information about zeta 1 by ODE means, but we don't have that anymore because it's a non-local problem. So we can't use just vanilla ODE problems. But with a lot of soul searching and a lot of dirty tricks, we were able to come up with an odd asymptotically sinusoidal function gamma 1, which basically is exactly like zeta 1 in every way that matters in what I described to you earlier, and is a small perturbation in an appropriate sense of zeta 1. I've normalized zeta 1 to have unit. Of course, zeta 1's only is a Jost solution. You can multiply it by 5 and it's still a Jost solution here. The way I've described it here, I've assumed that the L infinity norm of zeta 1 is 1. If you do that, then gamma 1 is a small perturbation in the L infinity norm of zeta 1. And it's funny. It's not just like a mu to the 1/2. Like this is an order mu perturbation. You might think that this would be order mu, or maybe even order mu to the -1/2 or something, or mu to the 1/2 here, but it's not. It's order mu to the 1/2 times the log of mu. It's quite a subtle calculation. And though we didn't prove that this is the sharp estimate here, everything that we did indicates that it's likely a sharp estimate. So, you know, when you see a logarithm showing up in your asymptotics, you know that it's a subtle problem. Okay. So anyway, we figured that out. That's basically the big guts of the paper, is understanding gamma. This gamma has all the same properties. It doesn't change the Fredholm properties of S mu. Everything I said before runs. Okay. So I don't know exactly when I'm supposed to finish, but I feel like I've got 5 minutes. So, and I will use them. So, all right. Now you've got everything set up. You've kind of got like all your things in place. Then you can kind of run your whole argument. Okay, so you solve for A using this sort of Lyapunov-Schmidt idea that came from the Beal point of view. Oh, I'm sorry, I'm talking about gamma here. The proof that gamma exists is just variation of parameters in Kato style perturbation theory. You have to work in a space of asymptotically sinusoidal functions. It's a bit of a chore, but it all works. Once you've got all that, then the sort of the coast is clear. You've got everything working out. You can solve all your equations. All the things that are supposed to be order mu or smaller or whatever actually are small. You just go through a bunch of contraction mapping arguments. You check that everything is small in the right norms, and you get your existence proof. So here's my one paragraph thing about why the ripples are so small. Okay, gamma 1 is this Jost solution. It's like zeta 1, and zeta 1 at infinity is like sine of x over the square root of mu. So one can view gamma 1 as being a highly oscillatory guy. All right. When you go into the equation, you find out that A equals the integral of gamma 1 times something that is a smooth function of x. All right. The Riemann-Lebesgue lemma tells you that, you know, if you integrate f of x times sine of omega x, and omega is big, then that thing is, you know, depending on the smoothness of f, that thing comes out to be like 1 over omega to some power, where that power is related to the smoothness. And we're working in a sort of a function space, and we can bootstrap, and that means everything's smooth, and you can do this Riemann-Lebesgue lemma. And so you do a sort of a bootstrap / Riemann-Lebesgue lemma thing, and you find that that A is is extremely small. At its heart, it's just the Riemann-Lebesgue lemma. Although of course it's not sign there. It's this funny Jost solution guy, and there's a bunch of work that you have to do, but it's all cool and it all works. Now let me talk a little bit about what Anna Weinstein, and I was on that team, but it was really Anna and Yuri Starosvetsky that did all the heavy lifting on this project, and Chris and his collaborators did. So you sort of study the same problem, but you take a different point of view, which is more classical asymptotics point of view. You know, Chris's is steeped in exponential asymptotics, and Anna's is steeped in special function theory, neither of which are areas that I know very much about. You try to get asymptotics for this exact same problem. And what was found is that at a countable set of values of the parameter mu tending towards 0, that the amplitude of the ripple A vanished. You know, I was going to go visit Chris in Australia a little more than a year ago. And, you know, these asymptotics and simulations that were done of these things are not fully rigorous. And so Chris and I were going to figure out how to do it. We were going to prove this conjecture, or maybe we were going to prove it. I don't know. We were going to try it. We were just going to talk about it. But then just 1 week before I was supposed to depart for Australia, there was a global pandemic. So that didn't get to happen. And I think someday we'll talk about it, but that day wasn't last year. So that's a big open question, is like, what does this amplitude vanish? It seems complementary to our result, where our theorem goes wrong at some points. There's these gaps in the values of mu that you have to avoid, but it's not obvious that they're the same. The gaps in our theorem, it's not clear that those gaps align with these places where mu equals 0. Maybe Chris can talk more intelligently about that. I cannot. So anyway, that's it. Thank you very much. It was a real honor to be asked to speak at in this session, and I'd like to thank Chris Howes and Chris Lustry for making it possible.
Thanks very much, Doug. Yeah, no, it was good to see that material again. I have a few questions, but I'll just open it up for anyone else first to jump in if they have any.
Great.
I think I have a bit of a chance here. A question that's become more significant to me on this topic in the last year or so is what to do. So you do make use of the fact that you've got this weakly nonlinear limit, weakly nonlinear kind of situation where you've got the sesh squared. And
sure, yeah.
There's these problems that don't have that are strongly nonlinear, no weakly nonlinear limits. And I mean, you can kind of, if you can prove that a solitary wave exists, I assume you can have some kind of ansatz, but how much does the method kind of break in that situation?
All right. So the question you're asking is exactly what differentiates this paper and this result from the one I did with Tim Favor. Okay.
Yeah.
So here, it's all about this operator S. So there it is. Okay. So we don't assume. Okay, so if you do the sort of the small amplitude problem, the weakly nonlinear situation that you're describing, this guy is not there, as it happens. Okay, this 2 sigma c term, it just isn't there, and so if it's not there, then that S mu is a much easier operator to understand. It's just a simple harmonic oscillator, and so. The argument in that paper it's basically the same sort of argument here, except that you have a sort of different small parameter. We call it epsilon. It's the deviation from the wave speed c, and this whole solvability condition is much easier. It basically winds up saying that you need functions to vanish at a particular all your all your functions have to be 0 at a particular frequency on the Fourier transform has to be 0 at a particular frequency. So, and this was the thing that really sent me and Aaron into a big tizzy, which is when we realized that we could not ignore this term. And so all this stuff I was talking about dealing with that sigma c there comes from that scenario. Now, so the question is, we don't assume that sigma c is small. We don't assume that c is too close to the wave speed. I mean, like I said, it can't be 5 million, right? But it can be, there's a point where it needs to be like less than 5 or whatever. And I don't remember exactly what that number is, but
I think you can get it out to 5 million if you really try.
I mean, maybe you need a. I mean, it all boils. It plays a role. The size of C plays a role in the heavy equation that I didn't talk about. This where did it go? See if we can find it.
Yeah, in our
I don't have it on this
analysis.
equation,
The heavy equation is a bit
yeah.
nasty.
The heavy equation requires C to be like less than 2.
Yeah.
Okay. But so now let's talk about all the pieces here. Okay. So what does you have to contend with the fact that sigma c is not small with respect to the small parameter. All right. And that plays a role in all this S stuff. Okay. You do need to use the weakly nonlinear limit kind of to get that the H equation can be dealt with. Now, if you were studying, say, the total problem, right, where you have, which I mean, could be done, then you actually know that the H equation, the linearization of the H equation near the solitary wave, you could probably get that H equation was fine in that problem if you had some sort of ghost of integrability lurking in the problem.
Yeah.
So you do need it, but it's not like it arises in the problem in a different place, and you can there may be ways to get around it if you have an integral structure lurking around. So the answer is yes, you need, in this problem it is in there, but there are sort of special settings where you could maybe get around it. And the big thing is dealing with terms like this. So let me tell you that if you look at the capillary gravity wave problem and you try to do the same argument, what's the analogous problem there? The analogous problem there, which is to my knowledge still unsettled, is if you take the surface tension in that problem to 0. So with the surface tension being positive, you have nanopteron solutions. That's Tom Beale's work, Shuming Sun's work, Eric Lombardi's work, Kinderlayer's work, a bunch of work on this beautiful, hard stuff. But the open problem there is sending the surface tension to 0, and do you get the pure gravity solitary wave? Nobody knows the answer to that. So yeah, there's a lot of interesting problems related to the limiting object. Is the limiting object order 1 or is it small? It changes the problem.
Yep. I have a second question, if that's okay, just based on sort of have you thought about this particular angle. I mean, you wrote that paper where you did the numerics and you found obviously the one-sided solid nanoptera, because if you shoot it into an undisturbed region, you're not getting oscillations on both sides. You're getting oscillations on one side.
Right.
And we've both run computations on that. We know that you can run that computation for a very long time without it falling apart. And I was wondering if your method has any insight on how that energy does eventually transfer into the wave to the point that the ansatz breaks down.
I have a lot of ideas about it, but it's not in this method. It's a sort of, that's more, so my current point of view is that problem is essentially a stability problem, not an existence problem, right? So this is an existence problem. There is a nanopteron, or there is a traveling wave, or whatever you want to,
Yeah.
however you want to view it. So that problem, which I, is my current, white whale, is treating that problem like a stability problem, but it is colossally difficult. So
yeah, we're trying an angle where we
I've done
start
it.
it from scratch and just basically numerically measure the amount of energy in the
Yeah.
tail to kind of get some numbers.
Yeah, I did that with some undergrads. I did something like that with some undergrads in this problem. I did something, I did some of my own numerics with the mass and mass problem, which is related, but not exactly the same problem. I did some for a simplified version of the capillary wave problem. It's you see that sort of thing a lot, and it's not well understood. So
Yeah.
when I have like a time free, I butt my head on it and get nowhere. Not nowhere. It's just real hard.
Yeah,
It's just real
agreed.
difficult.
All right. Does anyone else have any questions? Maybe we can end the recording now. Thanks very much for that.